So I won't say we played with things last week, but we seem to enjoy exploring the impact of electrostatics. Now we're going to actually find out how to do some math with some of those phenomena that you observed and see how we quantify what you saw and what was doing what. We're going to start with Coulombs Law, and we're going to start just fundamentally. So what Coulombs Law says is that if I have charge 1 and charge 2 in units of coulombs, separated by some distance squared, and multiplied by some constant, there's a net force exerted by this encounter. So this could be an electron close to a proton, this could be 2 protons, this could be 2 electrons, this could be any number of things. Yeah, we will. I'm trying to think of whatever other number of things it could be, but okay, we're just going to start with that. So K is this 1 over 4 pi times epsilon naught. Epsilon naught is the permittivity of free space. So we're actually going to get to a point where we need to worry about what this is, but for now we're going to begin with it just being permittivity of free space, so it's going to stay constant. You'll see that this can change and be something different. And so K is 9 times 10 to the 9th Newton meter squared per c squared. And remember, c squared, or not remember, but pay attention, c squared is not the speed of light, it's coulombs. And Q, our charges, are in units of coulombs. So it's important to make sure that you're paying attention to what units you're working with, so you don't have that kerboobled. And that's why paying attention to your units in the first place is so smart. So this first question we're just going to apply. We have a plus 25 microcoulomb and a 2.5 millicoulomb charge. They're 16 centimeters away. Now this is an inverse square law, so this force is going to decrease as 1 over r squared, so the further apart it gets, the faster it decreases because of this inverse square law. Let's see, a microcoulomb, 1 microcoulomb equals 10 to the negative 6 coulombs, and 1 millicoulomb equals 10 to the negative 3 coulombs. So that's nothing new. That's just going back to the days of the metric system, which we use. So now we're just going to apply this to that, and you're going to wonder, why can't we just do this all quarter? Let's see how it works out. So the net force experienced is our K. Well, we'll use numbers instead of just K. Is our 9.0 times 10 to the 9th Newton meters squared over c squared times our Q's. So 25, and it's positive. 25 micro, 10 to the negative 6. Ha! Not 11. 10 to the negative 6 coulombs times 2.5 times 10 to the negative 3 coulombs. All of that is divided by r squared, which needs to be in meters. So we are 16 centimeters away, or 16 times 10 to the negative 2 meters away. So 16 times 10 to the negative 2 meters. And that whole thing is squared. So you'll see this meter is going to cancel out with that meter squared. C and C, so that'll be c squared, is going to cancel out with that. And we will indeed be left with units of newtons. Cool. Phew! It's always good to double check. So now let's button push. And we'll write out the whole thing. 2197.2.7 newtons. Or we'll just do a little sig fig practice-ish. You guys seem fond of taking it out to 2. So we'll go 2.20 times 10 to the 1, 2, 3, 4, 10 to the 4th newtons. So those two little charges, a 10 to the negative 6 and a 10 to the negative 3, at this distance away, that's a pretty strong force. So I'm going to ask you this, based on what you saw in class, is this a repulsive or an attractive force, do you suppose? Think about it.